Okay, so let's get started. Right, last time we were talking about electrolysis. Just switch this one up a little bit. Hello, yep, that's better. Okay, so last time we were talking about electrolysis, and I introduced you to the concept of predicting what's going to happen when you put an electrode into two different types of ionic substance. The first one is ionic liquid, that is molten ionic compounds. Okay, so when you heat up an ionic compound to the molten state, and then you're going to get a molten ionic compound. And we predicted how we can obtain the products by looking at the compound itself. It's going to form the two ions, and the two ions will become the elements. Now, if you have water in the ionic compound and produce a solution, then you have to do some kind of prediction. Quiet down a bit, please. Okay. Okay. So when we have ionic solution, then we have to use the E values, these standard electropotential values, and there's a table there in the notes where you should have seen those tables. And we can use those values to make predictions. And our prediction is based on the rule that the more positive goes forward. So we have to select the two equations that we need, and then we have to compare the E values and choose the one that is more positive. Okay, so we have the reduction ones and the oxidation ones. We have to reverse the direction of the equations given in the list. So we have to also change the sign in the E values and then make our predictions. Okay, so make sure you reverse the equations, change the sign of the E values for the oxidation side or the anode side before we make our predictions. And we saw how the predictions actually could allow us to predict that bromine and hydrogen gas are formed, and which is the same as the experiment results. Now, we also did an example with sodium fluoride, and we predicted that we get hydrogen and oxygen gas. Now, the problem comes when we are making predictions in science. Sometimes we predict based on theories, but does it really work in reality? Not every time, okay? So there are certain examples where this prediction will not give you the correct results. And one of them is actually a very, very common ionic substance, which is just sodium chloride solution. Okay, so if you just take normal salt solution, and you want to consider the electrolysis of sodium chloride solution. So let's first of all start off by making our predictions and see what we would predict it to happen. Okay, so these are the predictions. So for the cathode, we know that it is the negative electrode. So the positive ion, the sodium ion from sodium chloride, will be attracted to the cathode. And at the cathode, we have reduction with a C, remember? Okay, so that gains electrons, give us sodium metal. That is the equation with the E value of minus 2.71 if you look at the list. So remember, we have this list here, and we can find that sodium at the top here has a E value of minus 2.71. We have water as the other possibility, reducing, giving us hydrogen gas and OH minus. That will have the minus 0.83, which is a more positive value. So we predict that we're going to get hydrogen gas and not sodium metal. Okay. Now for the anode, then we have to reverse the equations. Of course, at the positive electrode, the negative ion will be attracted. So we have the Cl minus going to the anode, and that becomes Cl2 gas. And for that oxidation, we have to look at this equation down here, okay, where we have Cl2, okay, plus electron going to Cl minus. Of course, now we have Cl minus going towards the back, okay, towards chlorine gas and electrons. So we have to reverse the equation, change the sign. So we have minus 1.36. And also the oxidation of water is given in this equation here, H2O going to oxygen, H plus and E minus. So in this equation, we have minus 1.23, which is the more positive one. So we will predict that in the electrolysis of sodium chloride, we will get hydrogen gas and oxygen gas. Okay, so these are the predictions made. So if you actually take out your salt from your kitchen, put some water in, make a salty water, and then put your electrodes into the bath, you're going to get a different product. Okay, the anode product is actually different. What you're going to get is in fact chlorine gas. Okay, somehow something is not quite right with the prediction. So here, instead of getting oxygen gas, the product is in fact the yellow-green chlorine gas. You can smell this. Okay, you can smell the chlorine coming from your salt solution if you ever did electrolysis of it. So the question is now, why is the prediction not quite right, and when can we trust and when can we not trust the prediction? Okay, so this is the wrong prediction. Now, first of all, you have to notice a few things. When we are making predictions, we have to predict based on a standard set of conditions because there are a lot of variations. You can change the temperature, you can change the concentration, and so on. Okay, so the first thing is all these predictions are based on the standard, okay, this word standard, electric potential values, and the sign here, the E with a little symbol, with a little circle with a stroke there, that symbol signifies it is under standard conditions. And in chemistry, we specify standard conditions as being under standard temperature, which is usually 25 degrees. And we have a standard pressure of 1 atmosphere and concentration of all the solutions at 1 mole per dm cube. So these are the standard conditions. So firstly, sometimes if we are deviated from the standard conditions, then we may have a different prediction. Now the second, in fact, if you even take sodium chloride solution and you did everything under standard conditions, okay, 1 m NaCl solution, 25 degrees, 1 atmosphere, you will still get chlorine gas and not oxygen gas. Okay, so it's not to do with standard conditions here. It's in fact, it is another factor which is to do with the energy barrier of the reaction. So this is a little bit of a thinking for you to understand what governs chemical reactions. Okay, a bit complicated, but when you have a chemical reaction, there are two things that governs it. The first one is the energy of the reaction. So we call that energetic thermodynamics. Okay, so if a reaction goes forward or happens, then there must be some kind of energy gain, okay, for the system. Okay, which means that in actual terms, we say that the energy of the system must decrease, okay, somehow, and increasing the entropy of the universe. That's the final effect of that, which is to do with second law of thermodynamics, and that's a lot of lecture that in order to understand that phrase, okay, but basically, the energy of the reaction has to be a favorable one in order to allow it to happen. So there must be some kind of energy gain, okay, overall in that process. You don't lose energy, okay. If there's a reaction that is not favorable in terms of its energy change, then it doesn't happen. But energy is only one thing. So our predictions based on the E values are based on energies. Okay, so we are considering the energy of these reactions, whether it is more favorable in terms of the energy to have sodium ions going to sodium or the water going to hydrogen. Okay, in terms of the energy, it is more favorable if we have the water going to hydrogen gas and OH minus, and not the sodium ions going to sodium metal. This is what we mean when we choose the more positive value. It means that in terms of energy, this is more favorable, and here in terms of energy, this is more favorable. Okay, so if we had the electrolysis of H2O and this H2O here as well, then we are going to get the maximum amount of energy from the reaction. However, if there's another factor that governs it, which is called the kinetic factor, which is about the rate or how fast the reactions are going. Sometimes some reactions, although it has a good energy output, but the reaction has a very large barrier. Okay, the barrier is not included in the energy change. So let me show you from this little diagram. Okay, so in terms of energy change, if we took the chloride and the water, then we have a smaller energy change than compared to taking the what is this? Wait. Okay, so this is the chloride and the water, and we're going to here forming chlorine gas or forming the oxygen gas. So we're comparing two reactions. This side, we're actually taking chloride and changing this into chlorine. Okay, so this is total energy for the before electrolysis with chloride ions and water. If we change the chloride part and form chlorine, this is not our predicted one, we have a smaller energy change. If we take the oxygen, the water, and form the oxygen and hydrogen plus, and you see the chloride has not changed. Okay, so if we electrolyze the water, then we will have a bigger energy change. This is what we mean by the predicting the E values. But if we actually consider the process, okay, this energy, this electrolysis of water has a large energy barrier, okay, compared to the energy barrier of the chloride ion. Okay, so in fact, this is easier for the chloride ions to be electrolyzed because it has to go through a smaller energy barrier. You see, in order to form oxygen and hydrogen, because water is probably to do with the neutral molecule compared to a charged ion. So a charged ion is sometimes easier to electrolyze. Okay, and here it goes through a very large energy barrier, and the energy gain is only a little bit different. Okay, so this is the main reason, because we have a large activation energy barrier here compared to that one. This is the kinetic factor. Okay, so this is called the activation energy, and the activation energy barrier is a bit higher in this case. Therefore, this is the reaction that we do not see happening, although by prediction, in terms of energy, this is a more favorable one. Okay, so you see chemistry, you have to understand that there are several factors that govern chemical reactions. And in order to understand this particular difference in prediction, so we have to go through the theory. Okay, so hopefully just to introduce you to this idea, not really for deep understanding into examination. I think you need to know a lot more about chemistry to understand this fully. Okay. Okay, so now you know that there are two considerations, and sometimes one can take over the other ones, and we have to see that the predictions that we make here are all based on energy considerations, but we did not take into account this energy barrier part or the kinetic part of the reaction. Okay. So why did I talk about sodium chloride electrolysis? Well, because electrolyzing salt water is very useful in the industry. Okay, so it is important to introduce this to you. But of course, if I introduce this to you, you will go back home and do the calculations, and you will come up with the wrong answers, and you will come up with questions. So let me tell you the answers before you have the questions. Okay, so the electrolysis industry, one of the biggest industry plant for electrolysis is to electrolyze brine. Brine is the name for salt water. And basically you get this for free. You just take water from the sea, and that is brine. Okay, seawater is basically sodium chloride solution. They will concentrate it a little bit so that it is more concentrated, and it would save a bit of electricity when you are doing electrolysis. So basically, brine is a free of charge raw material. Just take it from the sea, and there's plenty of it. And we can change seawater into very useful commodities for the industry. Let's see how we do this. So basically, an electrolysis cell. You can see this is the setup in the industry. There's a pipe for the brine to go in. Okay, this is a bit of a concentrated salt water, seawater. So concentrated seawater brine goes into the cell, and they are separated by a membrane. Now the membrane is there to prevent the gases from mixing. You see, both sides are producing gases. If we don't separate them, then we're going to get a mixture of hydrogen and chlorine, and that mixture is explosive, which means that if you don't separate, then your factory won't last very long. It will blow up very soon. Okay, so you have to separate these two parts so the gases don't mix. But the membrane is permeable to ions. So water molecules or small ions can flow through the membranes, but gases do not pass the membrane. Okay, so you can see the sodium ions can move over to the negative side because this is attracted to the negative side. Okay, so in the electrolysis, we saw that we have chloride ions breaking down to chlorine gas on the positive side. So here we have chlorine gas coming out. And here they use a titanium anode. Titanium is resistant to attack by chlorine gas. So they have a titanium anode, and then chlorine gas bubbles out from here. And on this side, we have a nickel cathode. And here, water will be electrolyzed to form hydrogen gas. So a lot of hydrogen gas will bubble out here. And then OH minus will be left behind. Okay, so we have a breaking down of the sodium chloride into chlorine gas, and also water is breaking down to form OH minus and H2. The sodium ions will be attracted over to this side because it's negatively charged, and also because we are producing a lot of OH minus. So it means that this chamber on the right here is getting more negatively charged because more OH minus will be produced as the water neutral molecule accepts electrons, okay, and goes away as hydrogen. So the Na plus will go over here to balance out the charge, which means we accumulate on this side Na plus and OH minus. And of course, they combine together to give us NaOH. Okay, so that's sodium hydroxide solution. Okay, so here we have sodium hydroxide solution coming out in this chamber from the production of OH minus and the accumulation of negative charge, and then pulling over the sodium ion so that they all gather in that side. Okay, so let's write down a little bit in our notes to annotate. Okay, so on this side we have chlorine gas. This is one of the products. And here we can write Cl minus okay, is forming Cl2 and losing electron. And over on this side, we have hydrogen gas, and this is to do with water, okay, becoming H2, gaining electron, sorry, and OH minus. Okay, so, and then here, a lot of OH minus will accumulate, okay. So the sodium ion will be attracted across. So we have a lot of Na plus here as well. Okay, from the other side moving over. Of course, gathering on this side as well. The Cl minus, of course, you can see will actually go over to this side. Any Cl minus actually goes over to this side so that it can be electrolyzed, attracted by the positive electrode. Okay, so at the end, we're gathering a lot of NaOH, and that becomes sodium hydroxide. Just NaOH. Okay, so we're producing three things: chlorine, hydrogen, and sodium hydroxide from seawater. Okay, so this is basically concentrated seawater. So all you need is seawater, one of these cells, and electricity. And you can start to run a factory producing three very important industrial raw materials. So any of you can go back and start a business tonight. Okay, so seems very simple. Now, why are we producing chlorine, hydrogen, and sodium hydroxide? Well, because of course there are uses. The name of this cell is a diaphragm cell, by the way. It's for information because it looks like a diaphragm. You know, the diaphragm in your lungs, which is a barrier against the gases, and this part looks like a bit of a diaphragm, the membrane there. So the gases don't mix here, and the ions can flow through. Maybe you can also make a note here. This is the membrane, and this is sometimes known as the diaphragm. Cannot spell this word. Okay, and then this prevents the gases from mixing. So you know that the chlorine hydrogen mixture is explosive. So this is quite dangerous. Okay. Full stop. Exclamation mark. Explosives. Okay. And it forms hydrogen chloride. So you only, if you mix up hydrogen and chlorine gases, you only need to expose this to UV light or sunlight, and then it will go with a bang. Okay, quite a nice reaction, but I don't demonstrate this. Too dangerous. Okay, so we are producing three raw materials just from salt and electricity. Okay, this is known as the chloroalkali industry, and it's a big industry. I mean, lots of investment and I don't know, $1 million industry. So we produce hydrogen gas, chlorine gas, and sodium hydroxide, and all of these are useful raw materials. Hydrogen is a fuel. Okay, we burn hydrogen at home. In town gas, we have half of our town gas is hydrogen gas. We use hydrogen to produce things like margarine, which is artificial butter, and margarine is not so healthy. So nowadays, because of the side product, which is trans fat, so don't take too much of that. Okay, ammonia is also produced from hydrogen gas. Ammonia is fertilizer. It's very important to, if you remember in the air pollution chapter, we kind of mentioned ammonia being sprayed onto the fields as it is a fertilizer for the crop growing. Okay, chlorine gas is useful for making disinfectants in drinking water. So you know, in swimming pool, when you go to swimming pool, you smell this chlorine gas, right? And also in most of the modern water supplies, you have chlorine gas added to the tap water. Like in Hong Kong, the tap water is chlorinated. So the chlorine gas is very important there in a tiny amounts to kill all the bacteria, all the bad viruses, bacteria, to make sure we don't suffer from an infection by drinking the water from the tap. And and in places where the water is not disinfected by chlorine gas, there's high rates of drinking water causing infections. Okay, so a huge problem. So we are we're lucky that we have chlorinated water. It's also used to produce plastics like PVC or some solvents, pesticides, and things like that. So chlorine, very important raw material. And sodium hydroxide, of course, is a basic ingredient for making soap or detergents, for making paper, making fabrics, and making cleaners, and also many other applications. It's the alkali of choice in the laboratory, right? So it has a lot of applications. Now you can even produce two other things from these. If you take hydrogen and chlorine together, and you can produce hydrochloric acid. So this is an industry that is not just limited to 3, but actually 5 compounds. You produce also hydrochloric acid, and from chlorine and sodium hydroxide, you produce bleach. Okay, so bleach and hydrochloric acid are also very important raw materials. Now, hydrochloric acid is produced if you take together the hydrogen and chlorine gas, and you would burn it. And when they burn together, they will produce hydrogen chloride gas. Now you see, we call the gas form of HCl hydrogen chloride. But when this is dissolved in water, okay, then we add water, then it becomes HClAq. This is now hydrochloric acid. So when it is in water solution, we call this the acid because now the ions forms H plus and Cl minus. But when it is a gas as a molecule, so the reason is this is a molecule, HCl molecule. Okay. But when it is in aqueous solution, this is H plus and Cl minus, dissociation, right? So this is the acid, this is the hydrogen chloride. The name is different. Okay, so we burn the gases together in a controlled manner to produce hydrogen chloride and dissolve this in water to form hydrochloric acid. Okay, so hydrochloric acid came from salt, from the electrolysis of salt. And to produce bleach, we have to take the chlorine and actually allow the chlorine to react with sodium hydroxide. So there's a reaction if you pass the chlorine gas into sodium hydroxide solution, and it will produce 2 different compounds of sodium and chlorine. The first one is NaClO. Okay, this is sodium hypochlorite. Okay, let's write down the name here. Sodium hypochlorite. Okay. Now, sodium hypochlorite is a compound of Na plus and a ClO minus ion. Okay, so this is the ions of sodium hypochlorite. This is the hypochlorite ion. This is the name. The name comes from the fact that it is a chlorite. Is, if you remember, the ITE ending tells you that it has less oxygen than the more oxidized one. So this has less oxygen than chlorate. Okay, there's a chlorate. ClO3. Okay, so that one is to do with a more oxygenated one. So with chlorite, it is less oxygenated. But there are 2 different forms of less oxygenated chlorine oxygen ions. Okay, there's a chlorite ion without a hypo. Without a hypo, it is ClO2 minus. Okay, so this one with ClO is even less oxygen than the chlorite. So we have to add a word in front called hypochlorite, which is telling us that it is the lesser one, okay? The one with the least oxygen. So ClO minus. So this is the oxidation of chlorine. You see from Cl from 0, oxidation number. This is element. Going to NaClO, we have changed this to +1. So Na is +1, O is -2, so Cl here must be +1. Okay, so we have undergone oxidation of chlorine in this forming of sodium hypochlorite, and this is the main ingredients of bleach. Okay, when you have a bottle of bleach, the active ingredient is sodium hypochlorite, NaClO. Now the other product here is sodium chloride. Okay, so it just also produce sodium chloride where the Cl is -1. So from 0 to -1, we have also reduced chlorine. So in this single reaction, in the single reaction here, chlorine is both reduced and oxidized, which means chlorine gas is both the reducing agent and the oxidizing agent. How interesting. Okay, so one thing is acting as both reducing and oxidizing agents, and one single species is both oxidized and reduced. And there's a special name when this happens. This is called disproportionation. So one disproportionation means the electrons are distributed unevenly. Okay, so if you think about this, from Cl to Cl plus 1, then you have to lose an electron. From Cl2 to Cl minus, you have to gain an electron. So somehow the electrons within the chlorine is distributed unevenly. One is losing, one is gaining electrons. Okay, so this is why the word is called disproportionation. Okay, not evenly proportionating the electrons. Okay, so this is the name given to a reaction when one species is both oxidized and reduced at the same time in the one single reaction. And this happens when we pass chlorine gas into sodium hydroxide to form sodium hypochlorite. Yesterday, there was an article that I wrote for HK01 for 香港01, and that was about the movie. There's a new movie coming called Logan Lucky, and in that movie, there is a explosion scene where the character takes bleach and then mixes with some salt and then with some gummy bears and throw it into something and then somehow explosion. And that reaction, they claim to produce sodium chlorate, okay, or potassium chlorate from the reaction, from mixing those things. But actually it doesn't happen, okay? So now, with understanding of oxidation numbers, you can explain why that is wrong chemistry. So you can think about that and maybe read the article if you're interested. So it's very much related to what we're talking about here today. Okay. Now, so now we have seen how the chloroalkali industry is very important. Okay, this industry takes only salt water. This is from the sea. Okay, and then you just need electricity, and you produce 5 very important raw materials. Okay, 1, 2, 3, 4, 5, and now you know how all these are produced. So we are going to move on to another type of use of electrolysis, which is to refine metals. So remember, this chapter is all about producing metals. So we have seen that we can electrolyze molten ionic compounds to produce some metals like lithium or magnesium, sodium, etc., aluminium. Okay, but we can also use electrolysis to produce some of the lesser metals or even to refine it. Okay, so for example, for copper. Now, copper is a very common metal, not a very expensive one, and it's quite unreactive. So if I ask you what is the best way to extract copper metal, by now, after a few lectures, you should be able to tell me that the best way to extract copper metal from copper ore is to heat it with carbon. Okay, to heat it with some charcoal or some coke or something, so that we can have a reduction. The copper oxide will become copper metal, and carbon becomes carbon dioxide. That is the cheapest and most efficient way to produce copper. But the copper produced in those ways is not very pure. The copper produced by heating the copper ore with carbon is only a rate maybe around 90% or less pure. Okay, so the block of copper, remember the guy, the old man talking in the movie and telling you about the copper mine in Canada and producing like a lot of exploitation potentials and so on, taking away that mountain. They're going to produce copper by heating the ore with carbon. But the copper produced will not be very pure. So if you want pure copper, you have to undergo a second process, which is using electrolysis to refine the copper we produce. How is this done? Well, it's done very simply. You just take the solution of copper sulfate or any other copper ions. So you have to produce the copper and then, okay, dissolve it in some acid, produce the copper sulfate. But you actually only need a single solution of copper sulfate. And then you need to pass electricity into the copper sulfate solution. So before we actually understand how to refine copper, let's start off by considering the electrolysis of copper 2 sulfate solution. So this is electrolysis of copper 2 sulfate solution. Okay, copper 2 plus ion with the SO4 2 minus ions, and then we have here some carbon electrodes. Okay, just normal, just like last time I was doing the electrolysis of potassium bromide. This time we are changing the solution to copper sulfate. So we have 3 different things present. We have the copper 2 plus ion, we have the sulfate ion, we have water. So we're going to consider the electrolysis of these 3 ions by E values. So of course we look up our tables. And then we find here that for the cathode, we have, for the negative side, we have Cu2 plus and water. So reduction of copper 2 plus or water. And you can look at the E values. Copper 2 plus will be here. Okay, so be careful here. Sometimes people make mistake. Let me just remind. There are 2 equations for copper 2 plus. One of them gains 1 electron to produce copper 1 plus. One of them gains 2 electrons to produce copper metal. Now you have to make sure you know which one you want to use. Usually it's this one with 2 electrons forming copper metal. So don't use the wrong equation or you will get the wrong answer. Okay, so don't lose marks here in the exam. Now, you want to take this equation plus 0.34, compare this with the reduction of water minus 0.83. So this is the more positive one, goes forward. So we get copper metal at the cathode. So here we'll see a layer of copper metal produced at the cathode. And at the anode, we are going to reverse the equation of the oxidation of sulfate ion to persulfate. So this equation can be found towards the bottom. So sulfate is very difficult to oxidize. So this one is towards the bottom. Sulfate going to sulfate. Okay, and then the E value is minus 2.01. But also water can be oxidized to oxygen, and that is minus 1.23 after reversing this equation. So this is the more positive one, and we predict that at that side we are going to produce oxygen gas. So this is what we see, oxygen gas bubbles and copper metal at that side. We understand this already. Now, how do you refine copper? Well, to do that, need to change. What we have to do is just to change the electrodes from carbon rods into pieces of copper. Okay, so here we're going to change this into copper metal, both sides, okay, and see what happens. So what we have at both sides is that we have now, at the cathode, we have the usual equation of Cu2 plus going to copper metal at the cathode this side, because copper 2 plus ion will be attracted there and it can form copper metal. So this piece of copper metal will grow bigger and bigger as the copper metal deposits onto the surface. So it will be bigger and bigger as you pass more electricity through the electrolysis. But at the anode, we have a new possibility. Now, previously in this with the carbon electrode, we only had water, copper 2 plus, and sulfate ions present. The carbon rods do not take part in the reaction. But here we have copper metal, so we have a new possibility of oxidizing, the copper metal. So we can actually oxidize copper metal as a new choice. Okay, this is the new choice here, copper metal being oxidized into copper 2 plus and losing 2 electrons. Okay, this is the new choice. We didn't have this before if we didn't have copper metal at the anode. Okay, so by having copper metal there, we have this, and we have to check the values. So at the anode, now we have 3 choices instead of just 2. We have the original 2, the sulfate ion, and the water oxidizing. So we know this is minus 2.01 and minus 1.23 when we oxidize these two. But we also have the oxidation of copper, which is the material at the anode. And the oxidation here, if we take this equation here, copper metal going back to Cu2 plus 2 electrons is minus 0.34 by changing the sign here. So here we have minus 0.34 volts. And if you compare all these 3 values, what do we find? Well, we find this one is the more positive one. So this is the one that will actually be most favorable in terms of energy. So this one goes forward, while these two don't take place. This one given priority. So in this case, when we change the anode to copper, we will actually see the copper metal dissolving, forming copper 2 plus. Okay, so now the copper metal is involved in the reaction. It will dissolve, form copper 2 plus ions. So this will become smaller and smaller, and the copper ion will go over to this side and gain electrons and become deposited here as copper metal. This side will grow. So we can now see what was going to happen. This will take place and the copper anode will dissolve. This copper cathode will grow larger. The blue color will not fade. Okay, the color before would slowly fade away as the copper 2 plus turns into copper metal. If we had the carbon electrode, the blue color of the copper 2 plus ion will fade away slowly as the copper is used up as metal. But here we have a constant supply of copper ions, and one copper ion produced, one will be producing the metal. So we have a constant concentration of copper 2 plus ion. Okay, and then this will dissolve, this will grow bigger. How can we use this to refine copper metal? Well, if we have an impure piece of copper that is from the production of copper by reducing with carbon, we can put this impure copper at the anode. And then we can use a piece of pure copper at the cathode. So as this electrolysis takes place in the bath of copper sulfate, the copper anode will slowly dissolve away. Okay, this is anode reaction. Copper dissolves to form copper 2 plus and 2 electrons. So all this copper 2 plus dissolves away, and then the copper 2 plus will travel to this side and grow bigger and bigger. So slowly we will dissolve away the impure copper and will grow the size of the pure copper, because only copper 2 plus will be deposited here. And any impurities in this piece of copper will either become dissolved in the solution, or it will be fallen down at the bottom as sludge. Okay, the sludge will contain precious metals such as silver or gold. So the question is, why doesn't the impurity also goes to this side? Why only copper 2 plus will travel there, but not, for example, silver or iron or gold or zinc or other metals? Why will they not travel over there? Let's look at the E values and explain how this works. Okay, so if you actually look at the E values and compare. My pen is here. Okay, so Let's think about this. So what we are trying to do is to choose the more positive value, and here is our reference. So copper going to copper 2 plus, and this side is minus 0.34 volts in the reversed direction. If you actually have another metal, for example, let's say you have impurity of silver. The silver metal, would it go back to silver plus in the electrolysis? So you had some silver and you had some iron, okay, in your piece of copper. Let's see what will happen to them. So here's the iron, here's the silver, okay. So if you do electrolysis, the iron going back to iron 2 plus will have a value of plus 0.45 after reversing, okay. And then this will have a value of minus 0.8 after reversing. So you can see that the more reactive metal, so iron is the more reactive one, this will actually go back to solution before the copper. So this will actually oxidize. So in fact, we will dissolve the iron into Fe2 plus. This will form. This will take place. If we had any silver impurities, this will actually be more negative than than minus 0.34. So this will not take place. This is more negative than minus 0.34. So this does not take place. So we just have silver metal not dissolving. It will not form silver plus, so it will just fall down to the bottom as a particle of silver. Okay, so they collapse at the bottom of the bath, all these silver or less reactive metals. So usually the metals which are less reactive than copper are precious metals, silver and gold and other precious metals. So they will actually fall down to the bottom, and you can collect those, and once you have enough amount of them, they will be worth some kind of money. So how about the iron 2 plus or other impurities, more reactive than copper? All of these lead and tin and zinc, all of these would dissolve in the bath. Would they become plated onto the copper? So we have to consider the other side, which is the production of copper, so the cathode. So at the cathode, we have, so at the anode we saw already that copper would dissolve, and here if you have more reactive impurities, like Fe solid, this would dissolve to Fe2 plus. This is more positive. This is what was it? Plus 0.45. So this is more positive. Yep. This is the shorthand for positive. Okay, positive sign and then VE. Okay. If you had less reactive impurities, like silver, and this one does not go back to silver plus. Enlarge this a bit so you can see what I'm doing. So this does not go back to silver plus because this is less positive, more negative. This is minus 0.8. This is more negative. So this one doesn't take place. This one will take place. And just for your reference, this one is minus 0.34 volts. Okay. So we see we'll have more reactives dissolved in water. This will become dissolved in solution. These will fall up as sludge. Okay. As Fe2 plus, this one, and this one as Ag, as the metal. Okay, just so you're clear about this. But then when you go to cathode, would you have, if you had also some more reactive ions, more reactive impurities dissolved, like Fe2 plus? So at the cathode here, if you have more reactive impurities, they will become dissolved. Would it go back to iron metal and mess up your purification? If you consider this reaction, In the reduction side, then this becomes minus 0.45. The copper one is plus 0.34 volts. So this is less positive, more negative. So this one doesn't take place, but this one take place. Okay, so you can see it will just remain in solution. So this doesn't take place, and this just simply remain in solution. So the more reactive ones will just remain in solution as an ion dissolving, and the less reactive ones will fall down to the bottom. Only copper will be the one that will be electrolyzed. Very clever, isn't it? So this is a very clever way to refine copper. Okay, using electricity, we're going to get purer sheets of copper at the side of the electrode, and all of these can be explained by potential values. Okay, so you can see this is a picture of the copper refinery. These are the impure copper anodes. You can see there are also plates of copper, but the color is a lot darker, and there are some kind of black bits and so on. So these are the impure coppers that goes in. This comes from the production of copper from heating with carbon and so on, contains a lot of impurities. And then these are the pure copper cathodes that comes out of the solution. A lot of copper is plated onto them, okay, and it's nice and shiny, okay. So you can see the scale again. I'm always amazed by the scale of these things. I've never been to a real factory. I would like to visit one if I have a chance. You can see this is the man standing here, the technician, and the size of these copper plates are much bigger than his size, right? And you can see how many rows of these things are there. Okay, it's like an endless trail of this bath here. So don't imagine how many liters of copper sulfate solution has to go in the bath, or how many tons of copper are being refined at this factory. Okay, so these are done in very big scales. And all this copper will come into your house as the cable wires, okay, as your coins, as other things that you're using with copper metal. Okay, so all of the copper started off with rocks, went through the production process, heating with carbon, and then went through refineries, electrolysis like this, before it goes into all these machines and things that you're buying, your iPads, your computers, your fridge, all these things that has copper metal in it. Okay. Okay, so I'm going to move on and tell you a different story of electrolysis. We can use this idea of passing electricity through a solution of ionic compound, to do some beautiful things. And one of the things that we can do is electroplating. Okay, electroplating is to use electrolysis to coat a thin layer of decorative metal or protective metal onto another less attractive metal surface. For example, if you go to the bathroom, you have all these shiny silvery toilet fittings. All these fittings, like the tap and so on, are plated with a layer of chromium. So chromium is actually the hardest metal. In terms of hard, we mean that if you scrub the metal against each other, which one will be scrubbed off, okay? So in terms of hardness, chromium has the greatest hardness out of all the metals, and so it's most resistant to scratching. So your kitchen, your toilet fittings are plated with chromium to give it a shiny appearance, and also it is resistant to oxidation, so it doesn't rust in the environment, the moist environment of the toilet, and it's very pretty and it's very scratch resistant. So it's for protection and for decoration. Gold plating is also very common. As you know, gold is very expensive, but a lot of people like the appearance of gold, or gold has some significance. For example, it is highly protective because gold is very unreactive. So you can have gold preventing something from rusting or from going dull or corroding. So we have gold plating onto this chalice. For example, this is a church, the vessel used by the priest in the mass, and the chalice is made of a base metal, for example, silver or copper. Or brass. So these are cheaper than pure gold. So of course the priest cannot afford the chalice of pure gold. That's too expensive. But you can have the appearance of gold by electroplating onto it a very thin layer, only a few nanometers thick of not nanometers, maybe micrometers. Okay, micrometer thick of gold. Okay, so usually the thickness is from micrometers to millimeters level, and And it would look very much like gold, and it has the protective behavior of gold from oxidation and from tarnishing and so on. And here is USB or adapter jacks, and you can see that a lot of these surfaces are gold colored, as you know. And in fact, these gold color are from real gold. So you probably have some kind of gold with you, okay? If you had some jacks and USB fittings. So these ones are plated with gold because not just for corrosion resistance, but because gold is actually a very good electrical conductor. Okay, gold is one of the best electrical conductors, and as you know, it's very important to have good connection. Okay, if your thing is corroded, then it doesn't connect very well. So that's for protection and for improving of conductivity. So how do we do plating, or how do we do electroplating? Well, to do electroplating, we have to choose, not every metal can be electroplated because it is also governed by the electropotential values. So the competition is usually whether you electroplate the metal or whether you oxidize water, because it happens at the anode, right? The ions forms the metal at the cathode, okay, so at the negative electrode. And at the cathode, you have to see that you want to have a more positive value than the reduction of water, which is here. So the reduction of water is minus 0.83 at the top here. So this equation is the reduction of water. And usually this will happen if you have a more negative value of the metal, like aluminium, magnesium, and so on. But if your metal, iron, has a reduction potential which is more positive than the water reduction, for example, zinc, or iron, or nickel, or tin, or lead, or copper, or silver. Okay, so all of these metals have a more positive value than reduction of copper, so these will become reduced instead of water. So you will form the metal, okay, at the cathode. So in those cases, you can electroplate zinc, iron, and nickel, and so on, and copper and silver. But you cannot electroplate things like aluminium or magnesium or sodium. Okay, so those will just never come out of the electrode. So you can see here we have a bath of silver nitrate solution, and you can put a spoon in. If you pass electricity through this, silver ion will be deposited on this side, and you will form a silver layer. Now, silver nitrate is actually not very good for electroplating because it also reacts with the spoon, and you will just get a black layer of silver coating. Indeed, you will get silver metal, but not very shiny. So usually we will use a different solution. I'll tell you in a minute. But just to understand the chemistry, there is we put the object to be plated as the cathode, okay, where the reduction takes place, and we have a bath of the solution containing the ion of the metal. So here, silver plus. So the metal will deposit onto it as a thin coating, and then if you do it properly, then you have a shiny, nice coating at the cathode. At the anode, what can we use as the anode? The anode is sometimes usually made of the metal that is being plated. So if you are electroplating silver, you would use a piece of silver at the anode because this will dissolve away the silver ion. So as you lose silver ion here, you dissolve back the silver ion from the metal, and then you can maintain a concentrated concentration of the solution here. So you see the anode dissolves, replenishing the solution with ions. So we can write equations to explain these. Here, Ag plus gain electron form silver metal. Here we have silver metal dissolving to form Ag plus plus electron. Okay, so these are the equations. So I also already told you which metals can be electroplated, and we have to look at the E values, which are those metals with reduction potentials more positive than the reduction of water can be electroplated, which means that we can electroplate things like zinc, iron, nickel, copper, silver, etc., but not things more reactive like aluminium or magnesium. So here's a bath of electroplating. So the steps to electroplating is usually where you would firstly have to prepare the object, because if you take a piece of metal, sometimes it's very dirty, like with grease or with other oxide layer and things like that. So you have to clean it with usually first an acid bath to dissolve the oxide, and then with base bath to remove the oil and grease. This is sodium hydroxide. This is some kind of acid like hydrochloric acid or nitric acid. So once you clean it, you will put it in a electroplating bath. And if you want to electroplate with silver, then you will have to use, or gold, most of the time we use cyanide solution. Cyanide is the Cn minus ion. And in Chinese, this is san ai. Okay, san ai, as you know, is very poisonous. Okay, it comes from the English name, direct English name of cyanide. Okay, and this is cyanide ion. And it forms stable complex with these metals, and actually it's very important to, if you want to form a silver coating of the silver or gold onto the metal. So a lot of the time, the electroplating solutions are very poisonous. Okay, so you have to be very careful when you're doing it. So you can write an equation like this: the complex ion with silver is AgCN2. This is the silver cyanide complex. Silver is 1 plus, but Cn is 1 minus. So if you have 2 Cn, gives you 2 minus plus 1 plus, overall charge is 1 minus. And this one also gains an electron, and this one forms silver metal, and the cyanide ions are freed. So here's a picture of someone doing silver plating in a small scale. You can see a small jewelry is being dipped into the silver bath, containing sometimes the new formulation don't have to use cyanides. They can replace this with other more fancy ligands. Okay, so here's silver plating, here's gold plating. And this one you can see is actually not a big scale gold plating. The only thing they're doing is to dip the solution of the gold ions into the cotton swab here, and they connect this cotton swab to an iron stick, which is made the cathode, and then the anode. And here they connected the cup here to the cathode. So the cup is the cathode, the minus electrode. This stick here is the positive. And when you touch this swab around, it will have a current, and electroplating will happen as you touch the thing around with the current passing. Okay, and gold is plated on the inside of the cup. You can see this is quite nice. Okay, you don't have to waste a lot of gold because the solution contains gold and it's very expensive. Okay, so not just gold metal, but gold in iron form has the same price as gold metal. So if you go and buy a compound of gold from a chemical company, they will calculate the price of the compound based on the market value of gold. They will tell you, okay, wait a moment, I'll tell you how much this gold sulfate or gold chloride is. I'll just check the gold price today, and I'll calculate and make a profit. Okay, so what I'm going to do now is to actually do a little bit of demonstration for you. So I will do some electroplating, and what I will electroplate is some of your objects. So I want to electroplate nickel. Nickel is a silver metal, silvery metal, and we can see here nickel is Ni2 plus, and it has an electropotential value of minus 0.26, lower than minus 0.83. So we can electroplate this, and oops, I have some nickel sulfate solution. So this is the green solution here, contains a lot of nickel ions. And I'm going to electroplate the nickel. But I will take your 50-cent coins. Okay, so I will take around 10. So if you have a 50-cent coin, you can find, and if you want it plated in the silvery color, I will take 10 of them and I can do electroplate it. So if you have one, find it, and the first coins that I put on the table, I will do them. Okay. So you can bring out one 50 cent, one each only. Okay. You can bring it out now. Okay. As a little souvenir. Okay, you can ask your friends. Okay, to pass it along, bring it out. If you want a silver 50-cent coin. I got $2. Okay, one more time. Any more? Okay. You can pass it to him. Here as well. Take those from him. Yeah, thank you. Okay, thanks. Okay. Yeah. I'm not plating the these are small ones. I don't play the small ones. They're a bit hard to electroplate. I'll return these. Okay. Okay, thanks. No, I cannot play the silver ones. I only take 50 cents. Sorry, I'm very picky. Okay, I'll take these. Okay, let's stop here. Okay. So how am I going to play this? First of all, you can see all these coins, some of them even from the British era. Okay, very dirty and old. So the first thing is to prepare the surface, right? Remember, the first thing to doing electroplating is to clean off the surface things. So what I'm going to use is nitric acid. Okay, I will use nitric acid to clean off the surface to make all these shiny coins, removing all your grease and the oxide layer. So the first thing I'm going to do is to put all these coins into the beaker here. I'll put this on the big screen so you can see what's happening. Okay. dirty coins goes in, nitric acid, okay, concentrated nitric acid, dangerous stuff. Mostly cleaned up. I think I still need to do a little bit more. Forgot to bring some tissue from the lab. Okay, so here you can see the coins after acid wash is all nice and clean. But there are some of them that still needs a bit of cleaning, I think, like this one and this one. Still a little bit on the surface. I will just get rid of these surface blemishes. Okay, so I think the coins are now pretty well prepared. Okay, so they're now quite well prepared. These ones are a little bit over corroded, maybe. Okay, in the past maybe they would charge me with defacing the queen, but now I'm safe. I'm not in a British territory anymore. Okay, so okay, so now I'm going to prepare my electrolysis bath. Okay, for this I'm going to put in my nickel solution. See, this has a beautiful green color, but don't drink this, very poisonous. And we're going to put a piece of nickel metal. The nickel metal will act as our anode. Okay, so we have our battery from last time. So we're going to use this 9-volt battery, and we'll connect the anode to the nickel. Okay, and then we will connect our coins to the cathode, which is the negative electrode. Okay, so now the first coin looks golden. The golden brass coin goes in. Just very briefly goes out, and it's now a silver coin. Okay, so you can see it's very, very quick. Just dip it in, and it's done. I'm going to repeat this, the factory now. So now let's look at the products and see how they are do a good job or did I waste your 50 cents. Okay, so now we have some 50 cents that you cannot use anymore. Don't use them. Okay, these are just for souvenirs. Okay, if you use them, I don't know if you get into some legal problems. It's not my problem. Okay, so I've now cleaned them. So now we have some silver coins. They don't look like 50 cents anymore. Some of them are a bit failed. This one also failed. Okay, sorry about that. Okay, these ones are good. These ones are shiny. You can see the place where the clip went onto has not been plated very well, so you can still see a little bit of copper color at the top where the crocodile clip was. Okay, anyway, you can come back and collect them. You had your coins given here. As well, one of them dropped. And hopefully keep them as a nice souvenir of our course. Thank you for your contributions. So the solution will go back to the bottle and we can reuse it. I told them that I can reuse this solution forever because the nickel 2 plus that I have lost in the electroplating have been replaced by the piece of nickel metal that I put in. So we will have a continuous concentration of nickel iron. And hopefully I can reuse this solution until I retire. Great, so we have seen how we could actually electroplate, and hope you enjoyed the demonstration. Come back to the lecture. So you can see electroplating is quite simple. You can just set up something in a beaker and you can do the electroplating. Now you can also electroplate onto something like plastics. Okay, sometimes you must have seen these things before. For example, for the girls, you have perfume bottles, and the caps in the perfume bottles are plastic, right? And they are usually silvery and golden. Okay, you might have ever wondered why you have a piece of plastic that could look like a metal. Or now it's Christmas time soon, and you can go and around town and you can see people selling these Christmas decorations. Again, they look golden or silvery, but then they are made of plastics. And for the guys, we have these moying, okay, the different toys, building some kind of crafts. And then these parts are also silvery, but then again, they are plastics. So how could you achieve the shiny metal coating onto a piece of plastic? Well, we have to do electroplating on the plastic themselves, plating it with gold or silver. But how could we do it? Well, plastic is not conductive, so we cannot put a piece of plastic in and expect the metal to deposit. But we can actually make the plastic conductive by chemically depositing a thin layer of metal onto the plastic. And we use a reaction called the silver mirror reaction. In this silver mirror reaction, we actually use glucose, and then we use this as a reducing agent with silver nitrate, so that it was actually reduce the silver ion back to silver metal and produce a silver layer. So actually a reduction reaction is happening here when we have a tolerance reagent of silver nitrate dissolved in ammonia, and this silver ion in Ag plus will be reduced back to silver metal, and this will deposit a layer of silver metal onto the plastic or onto a sheet of glass. And this is how they used to make mirrors. Okay, mirrors were produced in the past by having a piece of glass in this chemical bath of silver nitrate and ammonia and glucose, and then you can actually leave it there and a layer of silver will be deposited. So once you do this, for example, here you can see the lady is putting these plastic components into the silver mirror solution. and then the plastic will come out as a silver coating. So this is coated with a thin layer of silver. And then once you have the silver coating, you can electroplate the plastic as usual. Okay, so this is how it's usually done. First by depositing a very thin layer of silver by chemical reaction, and then doing the electrolysis. Okay, another thing that I might introduce to you is anodizing. So anodizing is a process where we actually produce aluminium oxide coating. So these are used for aluminium metal, anodizing aluminium, and it's used to color the metal. So for example, your iPods, okay, you see the surface of your iPods or some mobile phones have a nice color. And how do you actually color the metal? Because you know that the color is also metallic. Somehow you directly color the metal surface. And it's actually done by a very interesting process. So not natural aluminium is a very reactive metal, as I told you, and it would form an oxide layer instantly in contact with oxygen. So all of your aluminium products or aluminium metal will have a layer of oxide, but it's so thin that you cannot see it. Okay, so natural aluminium oxide barrier, which protects it from further oxygen and water, is only about 5 to 10 nanometers thick, very, very thin, and invisible to the naked eye. By an electrolysis process, we are going to increase this thickness of aluminium oxide up to 2,000 times the original thickness to around 10 to 20 micrometers thick. So you can see that by this anodizing process, we produce a thicker aluminium oxide layer, and also it's porous. So you can see it comes as little tubes, and there are some kind of holes inside. This is, do I have a picture of the micrograph? I don't have it here. Okay, so here I think you can see, if you anodize it and you can enlarge it, you can see all these oxide surfaces with little tubes, okay, with holes there. So it's a porous layer of aluminium oxide. How do we achieve that porous layer? Well, we actually place the aluminium object into a bath of dilute sulfuric acid. So very simple, dilute sulfuric acid in the bath, and then we use aluminium, the anodizing object, for example, the casing of the iPod, as the anode, this time the positive side, and then at the outside we put a piece of aluminium foil as the cathode. And the reactions that will take place, you can predict this from E values, is that at the anode we have oxidation of water. So when water is oxidized, you form oxygen gas, you form H+, and you lose electron. So oxygen gas is being produced at the surface of the aluminium. Now, the first thing that happens when you put the aluminium into the sulfuric acid before you actually start the current is that the sulfuric acid will dissolve the lateral aluminium oxide barrier. So the lateral barrier will first be dissolved by the acid very quickly. This is acid-base reaction forming aluminium sulfate and water. You know this already, neutralization. Once you expose the fresh aluminium surface, you pass the current, and then you have oxygen gas bubbling off the surface of aluminium. So having oxygen gas at the surface of aluminium will form aluminium oxide. So this is the reaction, aluminium reacting with the oxygen gas bubbling off during the electrolysis, forming aluminium oxide. And they will grow from the surface. But as you know, there are also bubbles of oxygen gas forming. So they will grow as porous layer because there will be some holes where the bubbles of oxygen gas can escape, okay, because it is faster to form the oxygen gas than to form the aluminium oxide. So some oxygen will be in excess and it will have to escape, and you will have some holes where the oxygen gas bubbles away. Okay, so it will become a porous layer of oxide, 2,000 times thicker than the natural barrier, but still invisible to the eyes. Okay, so if you want to see it, you still cannot see it by naked eye. You can only see it if you put it under a microscope. Oops. What did I press? Something goes wrong, or it's giving up. It's almost time to stop the lecture. It's complaining. Okay. Let me finish this slide. Okay. So it is forming little pores here. So what we can do with the little pores is that we can actually soak in a bit of dye. These are very concentrated dye molecules. The same dyes that's used for printing or for dyeing your clothes. We just soak it in, and they will take up the dyes into the little pores. So you take it out of the anodization, and you can soak it in a dye bath, and the dyes, the colored molecules, will go into the little pores like this, and then you can color the surface with the dyes, okay? You can coat it with the dyes, it will soak into all these pores, and finally you can seal off the pore. You can seal it either by boiling the aluminium, and the aluminium will form aluminium hydroxide at the surface, okay? The aluminium oxide forms aluminium hydroxide at the surface, and that will form a layer that seals off the dye and permanently sealing it inside. Or you can dip it into wax. This is a new method. If you actually seal the holes at the top with wax, the surface will appear very smooth to touch. So if you take your iPod, you know when you touch it, it feels very nice, right? It's a very smooth feeling. And that is actually the wax that you put on the top, some lubricating wax. So when you touch it, you feel very smooth. You cannot. You don't only anodize aluminum. You can also do it to other metals. For example, this is a coin commemorating the discovery of the DNA structure, and it's actually anodized niobium. So niobium is a common metal that is also anodized and formed in different colors. And here you can also see these body rings. I don't know, some of you, people put these in their tongues or around the body, strange practices. But you can make these out of titanium or niobium, and they could be anodized to different colors on the surface as well. So quite interesting things that can happen. Okay, so let me finish here, and we'll come back on next week. So we'll continue with the lecture. Is there anyone from Kitchen Destroyer? Because you asked me for thermometers, and I have some thermometers here for you. And also someone asked me for some droppers yesterday. Okay, you can come and see me.